So what's up, y'all? For those of you live in the room or those of you watching the YouTube recording, hello. My name is Whitney, or Whit. I teach the GRE and the GMAT for Manhattan Prep. And this lovely evening in late July, I am coming to you from Durham, North Carolina, where I live with my 3 dogs. And it's kind of a zoo here. It's very summer here right now. I live really close to Duke University, so if that helps put me in space, that way you know where I am. This evening session is going to be a quant focused session, and it's going to get really narrowly focused. We're going to look at exponents, and it's really going to be a huge exponent workout. So we're going to start with a quick quiz just to make sure that we're all on the same page with the standard exponent rules. And then we'll start messing with those rules in all sorts of ways that the GRE will throw them at you. One of the things to think about as we move along is that exponents are a topic that I think it's easy to improve upon if we give it a little focus. And no matter how hard they get, it's the same handful of rules. So that for me makes exponents and their cousin, the roots, a really effective kind of like quick hit topic to study. So if you're missing a lot of exponent questions when you're taking practice exams, it is absolutely an area where you can get some quick points just through occasional drills. Normally, I would not say to sit down and do an hour of exponents the way that we're about to. In general, once you've covered the rules, I would say that you want to cover exponents a time or two a week, give yourself some drills, and maybe do about 10, 15 minutes. I would say the same thing if you're trying to practice any of the rules like geometry. You don't want to just cram geometry for hours. You might want to do cover the rules and then see them little bitty windows of a time as you're studying. Cool. So all of our problems that we'll be working on tonight come from our own materials, and the vast majority of those come from our GRE 5-pound book. So if you're looking for additional practice problems, you can absolutely find that on our website as well as directly through Amazon, and have that either the physical book or an ebook version of it sent out to you. So lots of questions, quant and verbal, some pre-tests in there as well. So again, the official guide for GRE tends to be pretty slim in terms of additional practice problems. So we've got you covered. All right, so we're going to start with a bit of a quiz. So I'm going to kind of throw a minute and a half up on the clock, 2 minutes on the clock. Your job is to go through these questions and to try and see which of these are the rules that you feel comfortable with, and which of these are the rules that you don't feel so comfortable with. So like I said, I'll put a minute and a half or so on the clock, just trying to get a sense of which of these feels doable at this point, and then we'll chat about them together. All right, so that brings us to the end of our time just for this warm-up. Believe me, we'll be seeing a lot more. If there were any that you struggle with, feel free to send them to me privately in the chat window, but we're going to run through all of them together. So a little bit about exponents, right? There's often a lot of confusion around exponents when we get focused on just memorizing rules, as opposed to trying to understand what it is that exponents mean. And the fact is that this exponent notation is really shorthand. So if I were to say to you x to the 5th power, what I'm actually saying is that I've taken whatever the value is of x and I've multiplied it times itself 5 times. So x to the 5th is really a product of 5 x's, which then means that this x to the 3rd is just a product of 3 x's. Okay, so if we're dealing with a product of x's times another product of x's, PEMDAS, and our order of operations, would say that all of this is just one big multiplication, that these parentheses that we've wrapped around the 5 and the 3 x's are arbitrary. We could have just as easily have wrapped parentheses around 2 of them and then these other 6. Or we could have wrapped parentheses around 1 of them and then the other 7. And so the order that we do this multiplication is irrelevant, which means when I'm multiplying this big chunk of exponent with this big chunk of exponent, it's a giant multiplication. I'm multiplying 5 x's times another 3 x's. My total count would be 8 x's. The shorthand rule here would be to add. Right, so I'm going to add my 5 x's to my 3 x's, and that's how many x's I'm multiplying. Division is a little bit different. Instead of combining all the things that we're multiplying, when we start to divide, we're canceling. So same 5 x's, same 3 x's as our fraction, but this time, instead of multiplying them all across, we have several of these where anytime we multiply or divide, right, by the same number, those things cancel. So we take our original 5 and we cancel 3 of them. And this is how we get that shorthand of subtraction. So x to the 5th divided by x cubed is x squared. People start to confuse this a little bit when we look at raising this x to the 4th in this example to the 3rd power. That means that what I've done is I've written x to the 4th out 3 times. So if I were to list it, right, I wouldn't want to write this down every single time, but I do want to think of it as x to the 4th times x to the 4th times x to the 4th. And we saw from A that x to the 4th times x to the 4th, I would just keep adding up how many I was multiplying. So in this case, I would add up the 4, the 4, and the 4. This becomes a shorthand with multiplication. So if I raise a power to a power, that becomes a product. So those are our 3 core exponent rules: multiplying the base, dividing the bases, or if I have a thing with a power and I raise it to another power. All of these rules, mind you, require me to have the same base. So notice it's x to the 5th and x to the 3rd. It's not x to the 5th and y to the 3rd. The only way we can combine exponents in this way is if our bases are the same. So often what I want you to start to think about is with exponents, some little kind of side rules, is that many exponent rules require, or all exponent rules require, same bases or same exponents. And we'll see that example at the bottom. So when we have our exponent rules, we're looking for same bases, or we're looking for our same exponents. All right, now if I wanted x to the 0, I find that this can be really helpful to think about how we end up with 0 x's, right? If I were to think of x to the 5th as a count of 5 x's, x times x, right? Then x to the 0 would imply that we don't have any x's, that there are none. And the way we get here is actually through division. And the way this works is that when we multiply, right, like x to the 0, when we multiply and divide by the same thing, we end up just canceling out and having 0 things left. So for example, if I had x to the 5th and I divided it by x to the 5th, that would just cancel out to 1. But the math would also tell me that when I'm dividing, it's kind of like subtracting. And that's where my x to the 0 comes from. X to the -1 comes from the exact same idea. It's when I'm dividing, right? When I'm sitting there dividing, and what I'm dividing ends up with more in the denominator. So for example, if my numerator had X to the 4th, and my denominator had X to the 5th, if I listed out all those 4 X's and those 5 X's, I'd have 1 left over in the bottom. So the notation of like subtraction would result in a -1. The logic would result in 1 divided by X. 1 divided by X. So anything to the 0 power equals 1. Anything to a negative power has to do with this idea of a reciprocal where we flip. Just a quick note, we are not allowed to raise 0 to the power of 0 or to a negative power. That's not allowed. And the test will do a really good job of making sure that that 0 isn't an option for our base if our exponent is allowed to be 0. And the reason why we're not allowed to use a 0 to the 0 or 0 to a negative is because it would imply that we are dividing by 0. And that's one of the big no-nos. We are not allowed in math to divide by 0. It's not okay. Okay, so the first 3 rules are our biggest, right? Like those are the ones that show up most frequently. The next 2 are a little less common. So when I have my same base and I'm multiplying my bases, I can combine my exponents. When I'm dividing my bases, I can combine my exponents. And if I'm raising a number to another power, then I can combine those powers. But what happens when I'm adding? And the fact is that what this is X times X times X plus X times X times X. Let's look at this in real numbers just to see an example so that we can see that it's not just a simple combination. So let's say I had 2 cubed plus 2 cubed. I've seen all kinds of things that people have tried to do to put this together. I know that 2 cubed is 8. And 2 cubed is 8. And 8 and 8 is 16. And technically 16 is 2 to the 4th. Notice there's no way to just like combine, right, these 2 exponents to just magically get 4. So when we're adding our bases, because an exponent represents multiplication, we can't just smash things together. We just can't smash them together. So what do we do then? How do I get there from 2 cubed plus 2 cubed, right? 2 cubed plus 2 cubed, exactly right. There is no rule for addition. My only option is to either combine like terms or to factor. So often we'll see this X cubed plus X cubed. One way to think about it is if I have an X cubed and you give me 1, I now have 2 X cubes, right? That's how I'm going to add these, is to just add them as like terms. Alternatively, what I want to think about with the algebra, right, is if I could factor, it's just the same rules as a normal expression. Yeah, so if I factor out an X cubed from both terms, since that's the biggest thing I can factor out from both, I would get X cubed times that 1 plus 1. We could think about the distribute back through and prove that it would in fact come back to this X cubed plus X cubed. And so I get my 2X cubed. So if we go back to my example of 2 cubed plus 2 cubed, really what I could do is factor out a 2 cubed. That's a 1 plus 1. 2 cubed times 2. And all numbers, if they don't have a written exponent, have a assumed exponent of 1. And so when I multiply my bases, 2 to the 3rd times 2 to the 1st, that's my 2 to the 4th, which I know 8 plus 8 is 16. That would work. Okay. Last but not least, here comes my same exponent. This is the one place where we get a little bit of an exception, where the bases don't have to match, the powers do. In this case, my exponent that's cubed is on both my x and y. I can only do this if I'm multiplying or dividing. So the fact that I'm multiplying this x term times this y term, or if it was x cubed divided by y cubed, I am allowed to either do the exponent across them both or individually. So I can distribute this exponent, or I can factor it in a sense. So I could write this as xy and then cube it. Same would be true if I had x to the fifth over y to the fifth. I could also have that written as x over y to the fifth. If these were real numbers instead of variables, it might be that we would prefer to raise them to a power before we divide, or we might want to divide them first, cancel out some things so that what we raise to an exponent is a much smaller number. Okay, so if my bases are different, then my exponents have to be the same. If my bases are the same, I can do all the things that I want. So I want you to kind of keep this in mind. This is sort of my go-to reminder, is whatever is the same stays the same. And you're like combining the other part. So if the bases are the same, I combine my exponents. I don't change my base. The base stays the same. If the powers are the same, I don't change the power. I just change the base. So only one thing is going to change at a time. All right. Shall we? Are we ready? We're going to do a little drill. We're going to do a little quiz. And we're going to see what happens. Okay, so we've got a mix of some variables. I've stepped up the sort of complication a bit. So again, we'll take about a minute to solve all of these. Now that we've reviewed them, I think you feel a lot more comfortable. And then we'll start to really dig into some real problems. All right, so let's do it. Let's run through them. And I had a great private request about like, can you just give me a little bit more about this like bases are the same? So for all of these examples, these are all bases are the same. So notice in question 1, both of the bases are y. In 2, it's a, 3, it's 7, and so on. Right. So we're first just going to look at bases are the same. We're going to spend a little bit of time there. So what I mean by if bases are the same, we change the powers. I mean that in none of these examples am I going to try to make the base something different. So sometimes what will happen is that people will see 2 to the 5th and 2 to the 7th and think that they also need to combine the bases. So not just same bases, add my powers. So I've got 5 2s and then 7 more, which would be 12, but then also somehow change the base. So sometimes they'll call this like 4 to the 12th. That's what I mean. We only change the power. We don't change the base. This isn't going to be 4 to the 12th. We keep the 2 the same and just make the Cool. I'm glad that makes more sense. All right. And please, by all means, y'all, if there are ever any things you're like, okay, I'm head scratching about that a little bit, please put it in the chat window. That'll make life a lot easier, I'm sure, for everyone. Because if you have that question, so does someone else, right? So does somebody else. And if you have a question, put it in the comments on the YouTube video, because we'll answer those too. Fear not. All right. So if my bases are the same, if I'm multiplying 5y times 3 more y's, that's 8y. If I have a to the third squared, it's like saying a to the third times a to the third, or 3 a's and then 3 more. And so I've got a to the 6th. Now things get a little weird here. There's a couple of ways I can proceed with this. And so I'd like to see this in 2 ways. One is that I know that I'm adding the exponents when I multiply the bases. So this is going to be the same as 7 to the negative 4 plus 3, which is 7 to the negative 1, which we've learned is 1 over 7. However, we could have done the flip first. 7 to the negative 4 is 1 over 7 to the 4th. That times 7 to the cube, right? Third power. I'm going to write this as we're kind of a little more accustomed to it. That's 7 cubed up top, 7 to the 4th on the bottom. The 3 up top will cancel with 3 of the 4 on the bottom. And so we get 1 over 7, right? Or 7 to the negative 1. Same, either way. So if I have a negative 3 to the a and negative 3 squared, this one's a little strange. I'm going to leave the base as negative 3 for a moment. So I'll keep the base the same, negative 3. And then I'll take my numerator a, and I will subtract the exponent in my denominator, a minus 2. Now, technically, not that it's super helpful in this case, but technically I could write this as negative 1 times 3 all to the a minus 2, right? And now if we go to the same power, I know this is weird, this a minus 2, but that a minus 2 power is on both of those numbers. And so technically I could write this as negative 1 to the a minus 2 times 3 to the a minus 2. So that's this idea of if my bases are the same, these negative 3s, I can combine my powers. If my exponent is going to stay the same, which it does, notice I didn't change this a minus 2, it stayed a minus 2, it now just spread across the bases. All right, 3 squared to the negative 3 is the same as 3 to the 2 times negative 3, or 3 to the negative 6, which is also the same as 1 over 3 to the 6th. And in this number 6, I've got 2 x's multiplied by another 3 x's multiplied by another 5 x's for a sum total of 10 x's. And if I have 5 squared x times, that becomes 5 to the 2x. All right, so give yourselves like a little grade, right? Like how comfortable am I? Do I feel really good about these rules? Knocked it out of the park? Or is this an area where I really do have some room to grow, some space to kind of like spread and stretch and become better at exponents? That's the biggest thing when you're looking to study. Yeah, when you're looking to study, we're always looking for those opportunities to stretch. Oh, and a great comment privately in the chat window was, I got them all right, but I wrote the last one as 25 to the x. That's fine. That's not wrong at all. That's perfectly acceptable. It's going to depend on maybe what my answer choices look like, or what my next step in my computation might be. Like maybe I really need that base of a 5 to cancel out with some other things. Or maybe, and we'll see this here shortly, maybe I'm in a QC problem and I'm trying to make the two sides look the same. And so it might be fine to turn both sides into something with 25 or with 5. But yeah, this is perfect. There's nothing wrong with 25 to the x power. That's exactly right. That's exactly right. All right, so now let's incorporate a rule we haven't kind of talked about yet, which is what do I do when I have an equation? What do I do when I have an equation? How do I solve for things that have exponents? Now, the real key for this is what happens when I have variables in my exponents. So this is the crucial combination, is variables in exponents plus an equal sign, right, where I'm trying to solve. So the way we're going to do this is that we need the two sides to look the same as much as possible. And often what that means is factoring bases down. And often to primes. It's usually the kind of easiest way to get there is to bring them down to primes. So I have 3 to the 11th on the left-hand side. That's already a prime. So 3 to the 11th equals 9 is the same as 3 squared to the x power. So I have 3 to the 11th is equal to 3 to the 2x. Once I have my sides the same, I'm going to set the equivalent exponents equal to one another. So the 3 on the left has an exponent of 11. The 3 on the right has an exponent of 2x. And so I can just write the exponents down. The only way for this to be true is if the number of 3's on the left-hand side is equal to the number of 3's on the right. That means that the value of x is 5.5. This would not be considered advanced. What we're about to see will be, right? And this is why I love exponents. I love that you asked that. The reason why I love exponents is that even when exponent problems get really hard, it's not because the rules are hard. It's because they make us layer our understanding of the rules. These are the rules. We've seen them all now. These are all of the rules for exponents. So how does the test make them hard? They start to force us to see how to apply these in weird ways or make them kind of beefier and more complicated, right? For example, they give me something really ugly like this. So we're just going to practice kind of simplifying. So take a moment. How could we simplify this expression? Right? It might help to see the right side of the term as divided by 1. Right? But for this one, we're just simplifying. There's no solving. Two just quick comments that came through privately, one in the Q&A, one in the chat. And if you have a question, instead of the Q&A, if it's about something on the screen, go ahead and put it in the chat so I see it more readily. But if we have something like 7 to the -1 that we'd seen before, do we have to write it in one way or the other? Does it have to be 7 to the -1 or could it be 1/7? The answer is it depends. It depends on what the answer choices look like. If my answer choices all have negative powers, I'm going to make it look like that. If my answer choices have fractions, I'm going to make it look like that. There is no right way, just like the one with the 25. I could have written it as 5 to the 2a or whatever it was, or I could have written it as 25 to the a. They're both absolutely correct. Absolutely correct. They just look different. The other thing is that the only way to set powers equal to each other in that like equation is if the bases are the same. I can't do it any other way. But we'll see some kind of like some tweaks on that make it kind of a little fancy. Yeah. So now what I've got is I'm going to run through this entire numerator. I have m to the 8, p to the 7, r to the 12 times p squared, r cubed, m to the 4th, divided by m cubed, r to the 9th, p. I could start combining my numerator terms. So I have 7, 8, well, I'll start with my m's. I have 8, 9, 10, 11, 12 m's. Notice it's just a count. I have 7, 9, 8, 9 p's. and I have 12, 30 morning, 15 R's, all divided by 3 M's. I'll do these in the same order, 1 P, and 9 R's. Here's where I'll start my like subtraction or cancel. If I had 12 M's and you took 3 of them away, you canceled 3 of them out, that would leave me with 9 M's. If I had 9 P's and you took 1, I'd have 8. And if I had 15 R's and you took 9 of them, I would have 6. And that would be my simplification. And I'm not sure that like thinking of exponent rules as like commutative or associative properties would be terribly helpful. I don't know that I would think of them in either way. Then again, I haven't done algebraic proofs in a really long time. So good news, you don't need to do them for the GRE. But let's try another, right? Oh, and I had a great question. Let's see, let me get back. How did I get from the first green equation to the second one? Yeah, so the first green equation to the second one was combining all of that multiplication across the top. This is all multiply. Between every one of these is a times that, times that, times that, times that. And so just like if I had x to the 5th, x to the 3rd, I can just say I've got 5 of them and 3 more, that's x to the 8th. I can do that here. I have 8 M's and another 4 M's, which gets me to 12 M's. And I have 7 P's and another 2 that gets me to 9. And I have 12 R's plus another 3 that gets me to 15. Cool. All right. So now let's look at an equation again. What do I do when I have a variable in my exponent? This one's a lot more challenging. Now we're adding a new layer of difficulty. So I want you to take a moment just to kind of fight with it and see what you notice. Okay, so I know that when I have variables with exponents and an equation, in order to combine things or to set them equal to each other, I need the two sides to look the same. The problem is that on the left-hand side, I have a 2 and a 5. And on the right-hand side, I have a 20. So this is where I want to start to think factor down. So we're going to add a little bit of a factoring lesson. So if I've got 20, I'm going to look at this as a factor tree. So 20 factors down to 2 and 10. And if you haven't seen divisibility in a while, check out our YouTube channel. The link to our YouTube free prep hour YouTube channel is right here in the chat window. We have several videos on divisibility and factoring. So for this, I'd take 20 down to 2 and 10. 2 is a prime, so I'm going to stop there. But 10 can be further subdivided into a 2 and a 5, which means that 20 is the same as 2 squared 5 to the 1st. 2 times 2 times 5. So I now have 2 to the 18th, 5 to the m. Notice my exponents are different and my bases are different. There's like nothing to be done on the left-hand side. Equals, and now I'm going to write this 20 as 2 squared 5 to the 1, and all of that is now raised to the n power. All of that's raised to the n power. I can distribute that n. I can take one power and I can pass it across multiplication, or division. So I'm going to keep my left-hand side the same for now. So I'm going to write this as 2 squared to the n and 5 to the 1 to the n. Okay, keep the left side the same, 2 to the 18th, 5 to the m. 2 to the 2 to the n is 2 to the 2n. And 5 to the 1 to the n is 5 to the n. Okay, so what do I do now? What kinds of things do I combine now? Because I've got a bunch of different bases, I have different exponents. So I want to set equivalent bases equal to each other. So in order for the left-hand side to look like the right-hand side, or for them to be equal, there have to be the same number of 2's. In other words, 18 has to equal 2n. And in order for these two sides of the equations to be equal, the number of 5's has to equal the number of 5's. So in this situation, m has to equal n. Well, according to the first equation, the one based on the bases of 2, n, divide both sides by 2, is equal to 9. If n is equal to 9, then according to my second expression, so is n. So the answer to my question here is, what's the value of m? It's 9. Now we're starting to get into more complex topics. Right now we're getting into more advanced topics because they're forcing us to layer on a lot of these rules. All right, what about similar idea? Let's get you some answer choices to kind of play with this a little bit. What can I do here? And obviously, I could totally multiply these numbers out, right? I would have a calculator and off I go. But I want you to see, because notice my answer choices, whatever I multiply out, I'm gonna have to factor it back. So it might be better if I could just keep things in simple bases. Let's puzzle with this one for a moment. All right, so I want you to type to me privately. What do you think the answer to this one is? A, B, or C? Aha, very nice. Okay, so how am I going to combine these? I don't have the same base. So I need to make them look the same, but even then I've got this stupid plus symbol. So when I have a plus between things that have powers, I have to tread very carefully, very, very careful. Because, right, because when I am running through all these little pieces, if I have an addition, it doesn't play as nicely with multiplication. And that's what these are. 6 to the third is 6 times 6 times 6. 3 to the third is 3 times 3 times 3. So I'm going to rewrite 6 prime bases. I'm going to rewrite 6 as 2 times 3 to the third plus 3 to the third. Okay, so if I have all of these little pieces, then I'm going to distribute my exponent. I'm allowed to do all of this intermixing when all I'm doing is multiplying. So I'm going to rewrite this as 2 cubed, 3 cubed, plus 3 cubed. Okay. Well, I see that both of them have a 3 cubed in them that I could technically factor out. So let's try that. If I take 3 cubed and I factor it out, this first term would just be 2 cubed. The second term would just be 1. So I don't think the answer is going to be C, because C is really just 2 times 3 cubed. And right now I have 3 cubed times something way bigger than 2. But I only have 3 cubed times, I mean, this is 9, right? I can almost just write that one out. This is 9 times 9, which, wait for it, 9 is 3 squared, which means technically this is just 3 to the 5th. This is how the GRE makes things hard. Right? They start to hide things. This is how the GRE makes things hard. I got a lot of answers in the chat window and none of them are right. And that's perfect. That's what I want. This is exactly where we want to start to stretch. How can I start to pull like terms? So the biggest thing, right, here come some of your big clues that just in general, so here are your rules of thumb, so to speak. In general, exponent rules, you want either same base or same exponent. And you traditionally want multiplication or division. That's what you want. So now, interesting cases where you're like, oh, there's like a way to solve this, right? So your typical exponent rules work with same base, same exponent, and multiplication and division. Interesting cases are once we get equations, and especially if we have variables in the exponents. The other place is anytime we have addition or subtraction. Our only option is to factor or combine like terms. This is where they're going to get us. They're going to give us exponents in equations, or they're going to give us exponents combined with addition and subtraction, because we're not going to know what to do. Because sometimes, and this is where people get to see, and it's a really common wrong answer here, is like, well, I'll just make this 2 times 3 cubed. But if I were going to look, grab my calculator, 6 cubed, so 6 times 6 times 6 is 216. 3 cubed is 27. 2 times 27 is not 216. So they're going to get us in this like weird cases of equations and addition and subtraction. So I'd like to kind of focus a little attention there. We're going to see both, and we'll see a little bit more with our time today. But I want you to try that same thing here. How would I simplify this? 4 to the y plus 4 to the y plus 4 to the y plus 4 to the y. And send me your answer privately when you think you got it. How would I get 4 to the y? All right. Oh, and I just realized, y'all, sorry, there's like a side missing. Oh my gosh. Part of the question was hidden. I was like, this is crazy. All right. So hopefully you figured out the first half, how you'd simplify that. So no wonder you couldn't find an answer choice. Sorry. Forgive me, it's Sunday night, right? So I want to get this piece times, so this is multiplication in here. This piece. So I'll toss another 40 seconds. All right. So this is exactly what I was talking about when I say sometimes people don't know what to do. And so just start to combine things. And I get it, because it's like, I feel like there's a rule, so I should apply it. If my bases are the same, I combine my powers. If my powers are the same, I can combine my bases. But all of this requires multiplication and division. If I see a plus symbol, I can't just combine stuff. So I'm not going to add up my 4s to 16 and add up my 9s or add up my 3s to 9. Like that's going to be some sort of trap that they're hoping I fall for. And this isn't just going to be 4y. I don't even know what to do with this 12y business. I'm not even sure what to do. So let's actually do what we know, which is for these 4y's, and I can't just add them up. I can't just add my exponents. It doesn't work either. So what I'm going to do is say in my first term, I can factor out a 4 to the y, which would leave 1 plus 1 plus 1 plus 1. In my second term, I'm going to factor out a 3 to the y. And that's going to leave in here a 1 plus 1 plus 1. And I know my brackets and parentheses are all over the place, but forgive me. So I have 4 to the y. I should not be surprised that I had 4 of them. 4 to the y times 4 to the 1 times 3 to the y times 3 to the 1. Now I'm going to combine my powers. 4 to the y plus 1, 3 to the y plus 1, and then multiply, because that's how I had them. I had this y plus 1 and this y plus 1. None of my answers say 4 to the y plus 1 and 3 to the y plus 1. The only answer choice that has a y plus 1 power is B. And it's because the powers are the same. So I can do the multiplication first. So this would be 12 to the y plus 1. So this is back to that question about, well, would it be 5 to the 2a or is it 25 to the a? It depends on what the answer choices were. Right, so I've kind of always got to keep an eye on where I'm headed with the solution. But notice if there's addition, the only way I can kind of manipulate is through factoring or combining my terms. So for example, this is 1, 2, 3, 4. I have 4 to the y's. That's what this means right here. 4 to the y's. And I have 3 to the y's. Okay, so we're going to keep track of the fact that anytime I have an equal sign and anytime I have addition or subtraction, what I'm going to do is, slow down, try to put my pieces together. Okay. All right, let's try. Yeah, let's get some layering happening here. I'll give you the full time for this problem. It'll take about 2 minutes. When you think you have an answer, type it to me in the chat window, not the Q&A. So let's leave it out of the Q&A and just type it to me in the chat window. All right, so I've got a bunch of different answers and kind of all over the place. 11, 21, 5, 19, 27, 29. I love it. This is great. All right, so 5 to the 7th divided by 5 to the negative 4th equals 5 to the A. We can do this a couple of ways. One is that I can get rid of the negative exponent first, which would mean bringing it to the numerator. That's how we get rid of it. So one variation of this would be to say 5 to the 7th times 5 to the positive 4th is equal to 5 to the A, or 5 to the 11th is equal to 5 to the A. The other way we could do this would be to say 5 to the 7 minus a negative 4, because I'm subtracting. So it actually turns that into a positive that way as well. So this would be 5 to the 11th equals 5 to the A. So either way. So what do I know? I know that A is 11. So there's the first number, 11. To get B, I'll use the second one. I'm going to do the same thing. This time what I'll do is I'm just going to swap them. I'm going to bring the 5 to the negative 2 to the numerator to make it positive. And I'm going to take 2 to the negative 2. And I'm going to take 2 to the negative 3, bring it to the denominator to make it positive. And so I get 2 squared over 2 cubed is equal to 2 to the B. Or 2, so these two would cancel with these, this is 1 over 2 equals 2 to the, I'm going to write this as a capital B because my lowercase b's often turn into 6s. This is 2 to the negative 1. So B is equal to negative 1. Cool. So there's my next number. Alternatively, I could have said 2 to the negative 3 minus negative 2 is 2 to the B. And therefore 2 to the minus 3 plus 2, or 2 to the negative 1 equals 2 to the B. So either way, could have gotten there. Last but not least, I want to remember that this 3 has an understood exponent of 1. So 3 to the 8th times 1 times 3 to the 1st is now 9 3s. So 3 to the 9th is 3 to the C. Therefore, C is 9. There's my last number. So 11 minus 1 is 10, plus 9 is 19. Adding my layers, right? Adding my layers. You've now seen almost everything. Let's try one more. Let's try one more. Here we go. I'll put 2 minutes up. Nice, y'all. I'm starting to see a lot of answers coming in. So I have to get my bases on the two sides to be the same. So I'm going to start my factor. So 5,000. Well, I'm going to make it 50 and 100 because that's easy, or easier for me instead of like 2 and 2,500. Right. So I'm going to make 100, 10, and 10. Each one of these 10s is a 2 and a 5 and a 2 and a 5. 50 is a 5 and a 10, and that 10 is also a 2 and a 5. So I just need to be really careful here and count them up. So I'll start with my 2s. I have 1, 2, 3 2s. And I have 1, 2, 3, 4 5s. So my 5,000 can be written as 2 to the 3rd, 5 to the 4th, and that's equal to 2 to the x, 5 to the y. What that means then is that 3 equals x, 4 equals y. So what is the sum of x plus y? Well, it is 7. Nice work to those who gave me 7. Nice work to those of you who put an answer in at all because you tried. I love it. All right, so if you're looking for more exponents, we have an entire chapter in the 5-pound book devoted to exponents and roots. I know there was some question about roots. I just know that we didn't have a lot of time today. So maybe the next free prep hour I'll throw in some roots. But what I want you to do is take a moment to recognize that all of the rules that we applied were the same, like very small handful of rules. Same basis, multiplying, add the exponents. Same basis, dividing, subtract the exponents. If I raise something to a power to another power, I multiply those. If I'm adding, then I have to factor. And if the two sides of the equation have a variable in the exponent, then I need to break down my basis so I can set them equal to each other. From that, the GRE can make a whole wild mess of questions. It can get really, really hard. Really, really hard. But it's the same core rules. And I find that most people get hard exponent problems wrong because they don't feel solid with the rules. And as soon as things start to look a little different, they start applying rules and kind of like, oh gosh, what do I do, in a panicked way, right? And they stop following the good rules that they set for themselves. So one of the things I would say is look for, right? Again, we have like a chapter in our 5-pound book. We've got these in our strategy guides, right? Like we got exponent problems everywhere. We're not the only ones. The internet has exponent problems everywhere. Just make sure you say like GRE exponent problem. But try a variety of difficulties. Look for all the crazy patterns that you can find. Yeah, like all the crazy patterns that you can find, right? And try and apply the handful of rules. Say, these are my rules. These are my like 7 rules. What does it look like to apply them in this problem? You may have to do a various combination, kind of weird layers, but I have faith in it again. Again, if you are looking for more from us, our free prep hour site is phenomenal. It's phenomenal. But if you're looking for our site at all, we have an awesome site on YouTube, our GRE site on YouTube. I'll put this here for you. Send it out to the room. On this YouTube channel, not only do we have our free prep hour entire playlist, which at this point, I believe is up to, oh my goodness, so many. We have 75 videos that are all an hour or longer. So you have so much that you can cover. And in fact, maybe a couple of years ago, we already did an exponent. So if you want more practice, but different, there's an exponent one way down here somewhere. It's kind of old, but you can find it. There it is, exponents. My friend Kat did that one. She's great. Also on our YouTube channel, if you're looking for vocab practice, we have 2 channels devoted just to vocab videos. So we've got our vocab word of the day 2020, and then we have our earlier vocab word of the day that is from 2019. Each of these has 150 plus words in 45-second videos with little tips and tricks to help you remember them better. We got all kinds of stuff for you on our site. So definitely follow that link if you'd like it. If you're already on our YouTube channel, you can just kind of click to get back to our playlist. But otherwise, it has been a pleasure to get to work with all of you this evening, both live and online. I want to wish you the very, very best of luck with your GRE preparations. Again, if there's anything we can ever do for you as a company, know that you have access to a lot of free resources. You can take a free practice exam. You can sign up for any session 1 of a full course for free online. You just go to our website, manhattanprep.com, right? Sign up for any session 1 live class. Once we're back in person, you can sign up for those as well. But for now, they're all online. So you can always sign up for those. And you can try those out just from manhattanprep.com. You'll see a link for GRE and free stuff, or you can follow the link that I just put up there. And otherwise, hopefully we will see you around the GRE water cooler, and good luck. Nice work tonight. Thanks, everyone. Have a wonderful rest of your evening. I'm super glad to have gotten to spend it with you.